Welcome to today's SCA webinar with Everton Araujo of Subsurface Alliance on the geomechanics of carbon capture and CO2 and storage. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. And so I'm going to launch a couple of polling questions. The first question is, what is your primary discipline? So we see we have quite a few geoscientists in the audience. A few petroleum engineers have joined us as well. The votes are still coming in. We're at 77% geoscience. We have a few petrophysicists, a few in the other category. We're still getting responses from those of you who are still joining us. Still getting responses. I'll go ahead and close the webinar now and share the results. We have 73% geoscience, 22% petroleum engineering, and 2% petrophysics and 2% other. So the next polling question is, how many years of full-time experience do you have in the upstream oil and gas industry? We have quite a few people with over 30 years experience. We're getting more responses here. Thanks for voting. And it looks like most of you have voted, so I'll go ahead and close and share the results. 31% are in the middle, 11 to 20 years experience, followed by 27% with over 30 years and 22% with 1 to 10 years. And we do have some in each category. So that's a great group. So before I introduce Dr. Araujo, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature, and we'll cover the Q&A at the end of the presentation, and you will be anonymous. So today's presentation is the geomechanics of carbon capture and storage. And Dr. Araujo is a geomechanics specialist. He's worked for a number of employers, including Geomechanics International, Equinor, BHP, where he served as principal in geomechanics. And he has expertise in all types of geomechanics-related topics. And so you can see his credentials. He has received his BS, MS, and PhD, all in civil engineering from different universities in Brazil. So Dr. Araujo represents the Subsurface Alliance, and he'll be speaking today on the 3 pillars of carbon capture and storage: the capacity, the injectivity, and the containment. And Subsurface Alliance is a network of subsurface specialists that have worked together and are today offering comprehensive subsurface solutions in a team-of-team approach. In this case, we'll be talking today about CO2 storage, but there may be other topics related to geomechanics in which you'd like to employ their expertise. So you can see some of those listed there. In the future, SCA has some live online classes that are scheduled for the first quarter of next year. We have Srini Prasad speaking on maximizing upstream oil and gas exploitation values, and he'll also be doing a different class on developing robust production forecasts. Both of those live online classes are offered in January in half-day formats. And then we have Bob Barbet speaking on best practices for new well fracs and legacy well refracs. That's offered over several days in January and February. And then we have Dr. Larry Lake and Dr. Jerry Jensen, who will be speaking on managing mature oil fields with CRM, capacitance resistance modeling. That's a total of 16 hours live online, offered in half-day formats. And then Dr. John Lee. He has 2 classes, production forecasting for low perm reservoirs and the PRMS and SEC reserves and resource regulations. Both of those are offered in half-day formats over several days in February and March. Looking ahead for free webinars that are coming up in the new year, we have Fermid Fernandez, also of Subsurface Alliance. He will be speaking on excess permeability in carbonate reservoirs, curse or blessing. And then we have another CCUS topic from PK Pandy of TIER. He'll be navigating CCUS, the landscape, historical context, opportunities, and participation. And of course, SC offers training classes that can come to your location to be offered in-house, or you can attend our public classes. So there's a phone number and an email address that you can contact us for more information about training. And choose SCA not only for your training needs, but for all your projects and studies, consulting, and direct hire needs as well. And so without further ado, I'm going to give the presentation rights to Everton, and it's all yours.
All right,
we can see your slides.
Thanks a lot, Susan, for the nice introduction, and SCA for the opportunity to be here today to share some aspects of this very popular subject right now, which is the carbon capture and storage. And this is a very extensive topic, but we're going to try to give a good flavor of what geomechanics is and how to apply it to the CCS projects that are ongoing right now, and some that are in planning, evaluation, feasibility stages. So, as was showed as an introduction, usually we speak in terms of these three keystones of a CCS. The first thing that every single project is going to look for is the size of the subsurface container that's going to be available for the amount of CO2 that we want to inject and keep stored for hundreds of years. So people are going to start looking at, let me get the pointer, the capacity in terms of the pore space, the extension of that intake formation, the structure, if the formation is going to be heavily faulted or not faulted or near complex geology, and the thickness. So at this stage, geomechanics not necessarily is needed, because we are just evaluating how much space we need and how much we can find available in the local geology that we are planning to develop the project. However, as we move into the second stage or aspect of the project, which is really thinking about the injectivity, we start having features that geomechanics really plays a role. We need to find out about how much is permeable that rock that we're going to be injecting, because we're going to have to decide the injection rates into that formation. We need to find out the original fluid pressure. Are we injecting into a virgin saline reservoir, or is this an old field that has been depleted? That injection pressure has to be aware of what is the fractured pressure of the intake formation and also the sealing formation or the cap rock. The well operability, we need to make sure flow rates and any operations related to the well operation are going to be safe and not going to allow leakage and fracturing and things like that may create some safety operational features here. And also, we need to understand if the CO2 are going to go in streams through natural fractures or through matrix, and how further and fast the plumb is going to be extended. So in these three keystones, geomechanics really start playing a role in the second one. And as we move to the last one, which is not least important, actually kind of is the primary when it comes to the safety or risk assessment, because the main idea of the CCS is that we want to keep the amount of CO2 that we injected contained. We don't want any leakage, any migration to undesirable locations. So we really need to think about our seal integrity, which is the cap rock. If the faults are there, and they are always there, some cases more, some cases less, some cases the faults, they die out in the reservoir or they propagate across the cap rock, sometimes all the way to the ground level. Natural fractures, are they contained only to the reservoir, or are they kind of a connected network through the reservoir and also the cap? If the amount of volume is going to be creating amount of pressure that's going to be enough to create deformation that can go and propagate all the way to the ground surface, which will be reflected as a surface heave. Seismicity is a very good topic these days because since we kind of had the shale revolution in the US, we have been disposing tons of wastewater, and you have seen seismicity increase in places like West Texas that was really quite a few decades ago, and right now, I think last month we had a 5.0 magnitude earthquake. The well integrity, which is the core and most important thing in this project, because most of the time the problems start at the well or near well bore, because the stress concentration and disturbance is really great at this location just by the presence of the well. And also monitoring, what kind of monitoring we do in kind of a couple together with the geomechanical modeling. So as a way of give an idea of what are the guidelines or recommendation suggestions. In the United States, the EPA, or the Environmental Protection Agency, has established in his 2013 document for the Class 6 wells some recommendations, requirements, which is actually the most strict when compared to regular oil and gas wells. For example, here there is the topic of 2.3.6 geomechanics characterization and what type of data to collect. And they mention a lot about fractures, how you detect fractures, how you should characterize them. You should have a good understanding of your rock deformation and strength, because operations you're going to be doing, you're going to be increasing pressure, you're going to be changing temperature, and these things are going to put the rocks at stresses. And this can become excessive. If it becomes excessive, we're going to go into a rock failure, and we don't want that scenario. So the in situ stress field is a primal type of geomechanics feature, because without the geomechanics in situ stress field, which is the vertical stress and the two horizontal stresses, we cannot really do the calculations that is required in geomechanics, like the cap seal integrity, the fault stability, the well integrity. So we need to understand the in situ stresses, which includes also the pore pressure, not only in the reservoir, but also in the cap rock. So here are the EPA guidelines, and I'm sure all the countries have similar, different, or maybe more restricted recommendations. When it comes to that type of data required to go and characterize every single element of the geomechanics model, the EPA also provides a good a list of data and modeling that should be done and carried to be included in the permitting process of a CCS project. This picture kind of gives a cartoon-ish type of idea of what we can expect of a CCS project when it comes to the geomechanics. We are essentially to going and bring down a good volume of a CO2, and that CO2 volume is going to create a plumb that is going to extend. And if your reservoir is not extensive enough, you're going to start seeing increasing in the pore pressure. Also, the CO2 comes down with a much cooler temperature than the in situ temperature of the reservoir, and that's going to create a cooling effect. That combination of increasing pressure and decrease in temperature is going to add up to the in situ stresses, and that can create excess stresses that can put the rock at the probability or feasibility for failure in both tensile, which can be a fracturing formation. Usually you can see that it's starting near the wellbore, but can also start away from the wellbore if you have, for example, faulted region or naturally fractured region, and that can be facilitated by this increasing pressure. And if you have minor faults that are really maybe not even visible in the seismic data, for example, and those faults get, for example, activated by the increased pressure or decrease in temperature, you can have migration outside of the reservoir into the cap rock, or maybe at the shallow formations where you may find some ground potable water, which is not really desirable. Or in the worst case scenario, if major faults are really connected and it extend all the way to the surface, this can be induced seismicity case in case the fault gets reactivated, which is going to turn into a preferable well flow path for the migration of the fluids from the reservoir all the way to the surface. And we're going to see example of these two type of features in real cases that are really kind of happen and how this has been kind of addressed most recently from two projects in CCS. So for geomechanics, like I mentioned, we need to have an understanding of the present day stress state. We know that when we look at the seismic and we map faults, we see normal faults, we see strike slip faults, and we sometimes see thrust faulting too. But those faults were created in the paleo stress environment. And it does not really mean that today we still are under the same stress state, because the tectonics evolves, and we may have normal faults mapped in the seismic, but we may be at the present day at a strike slip condition. And those conditions are established by determining or constraining the three magnitudes of the three principal stresses: the vertical stress, the maximum horizontal stress, and the minimum horizontal stress. So depending on the arrangement of these three stresses, we may be at normal faulting, where vertical is the greatest stress, or strike slip when the vertical is the intermediate, or maybe in a reverse faulting when the vertical stress or your overburden stress is the minimum stress. So very critical, and this is part of the geomechanical assessment risk. You need to build the model to constrain these three stresses. Also, you really need to understand if this is, for example, in a case of a normal faulting where your vertical stress is the greatest, and this is going to be maybe your reservoir that's going to intake the CO2 volume. We also need to understand the difference of stresses in the reservoir layer and the cap, because that can be a source of weakening point for when we start doing the operation. So the model is not only for the reservoir, but really for the overburden, and sometimes even to the underburden if you are getting close to basement or some faulted regions that can be connected to the basement. So the pore pressure prediction is very well established the way it has to be constrained. So this is an example of a typical well, when we can have well logging data like sonic data, resistivity, density, and we can establish for the overburden or the tight formations where we cannot measure pore pressure, we can establish what we call normal compaction trend lines and see when there is a deviation from that trend line, we can infer that, oh, there is an abnormal pressure here, overpressure. Or if we are in permeable formations like this scenario here, this would be like a sandstone, we can take actual measurements from the well and kind of find out at the end, combining the calculations from the well logs plus the measurements from the well bore, what is the pore pressure profile, which is part of the geomechanics assessment. Also, and very important, if we are going to do CCS in depleted reservoirs, we do need to understand how much is the pore pressure right now and how much it was in the beginning before that field, that reservoir was depleted, because this delta P in time have created a delta stresses, which we need to account for. So we're going to start operating a reservoir that's not at the virgin conditions anymore, and we need to understand that. So here's an example of putting together a model with the pore pressure here in blue, and you can see that at a certain point at 2,000 meters depth, the pore pressure starts going a bit higher. It's not hydrostatic anymore. You have your lithostatic or the overburden, the minimum stress that has been established through fracking measurements at a certain points, and some sort of modeling that creates ranges for possible maximum horizontal stress. Currently, there is no way to measure maximum horizontal stress. You do have to do geomechanical model to understand what is the most probable range for that parameter. So as I was speaking on the previous slide, so the variation or the change in the pore pressure will create a change in stresses. So this is a typical pore elastic equation that shows that if we have a delta P, and given the elastic properties of that rock that we are changing the stress, our stresses are going to be changed as well. So if we kind of just punch here typical parameters for the alpha equal 1 and the Poisson ratio 0.2, a change in delta P can result on up to 75% in changes in horizontal stress. In other words, if your pore pressure depleted by 1,000 psi, your horizontal stresses can reduce up to 750 psi. And that's variation and change we call in geomechanics a stress path, is how your stresses are moving a long time as we produce, extract fluids from the reservoir, or we inject, putting fluids into the reservoir. Maximum horizontal stress orientation is usually determined by looking at borehole image data like FMIs or other types of image data that you can see and identify borehole breakouts or drilling-induced fractures. So this is very established technology in the oil and gas industry, and most of the wells today, they collect this, not exactly for the purpose of geomechanics, but we do take advantage of the availability of this data and find out about the stresses. For example, this is the orientation of the maximum horizontal stress given by the orientation of tensile fractures that have been observed here, and also the breakouts, which are 90 degrees apart from the orientation of the drilling-induced fractures. Looking into the rock mechanical properties, we need to understand how these rocks are going to deform, and ultimately, what is the maximum strength that these rocks can exhibit once we are doing changes down there in the subsurface. So usually we take core pieces of rock to the lab, and we simulate there in the lab a loading stress on those little plugs or samples of the rock to expected range of stress that we're going to see down there in the subsurface. And then we determine how much that rock is strong. For example, here we have a combination of log-derived properties, which are calibrated to lab measurements. And then you see here a profile for rock strength in case of shales, the dark rocks here, and the yellow or the sandstones in this case. And our target here would be more or less at this level of 3000. So where our reservoir here, you can see that has a much stronger rock than the overlaying cap shale. So this is something to be very aware. So this is something that a good project should extract core for geological properties of determining porosity, permeability, but also the mechanical properties. However, not only the rock in its in situ condition is the one that matters. If our rock that is the primary rock in the reservoir that's going to intake the CO2, we may have some changes in the composition of the material because of the CO2 brine or environment is going to create an acidic situation. And that acid may start destroying the cementation in between grains, which will result in reduction of the strength of the material. In this case here, we have a limestone that this is a typical result from a compression triaxial test in the lab, where you apply a deviatoric stress, and then you record the strain all the way up when the material fails, and you can say, okay, this is my ultimate strength, and the slope of that straight line would be your Young's modulus or your deformation elastic parameter. So after treating that material for a couple of days with CO2 and repeating the test in another sample, of course, you really see that the strength has reduced and also the deformation parameter. So putting together a set of 5 or 6 tests here, you can obtain what we call a strength envelope, how much we can get a shear stress and make the rock to fail. You see that this limestone was really kind of at this level of strength here, and after the treatment, a significant drop happened. It's really kind of an interest because once your material change the mechanical properties, you're going to have more deformation happening, and eventually you're going to have failure happening at before levels that you were expecting. So you need really to be aware of that. If your reservoir is going to be prone to this type of alterations, you need to do this type of test too. If by any chance we're going to be close to complex geology, for example, if you're into looking at saline aquifers or depleted reservoirs in the Gulf of Mexico, where we have a lot of salt diapirs, for example, these kind of a complex geology usually disturb the stress field. And the best way for us to account for that is usually using 3D finite element models that can really calculate not only the magnitude, as you can see here in the color scale, but also how the stress is going to tilt or reorient depending on how much the salt tectonic is going to affect that stress. You can see that at this orientation here, or this location, the principal stress is still kind of vertical. That would be a sigma 1. But as you start getting close to the salt diapir, that's same stress start rotating, and eventually it's not becoming anymore your sigma 1. So complex structures like salt diapir or heavily faulted regions can really suffer from this type of stress disturbance, and we need to account for that too. Now looking to one of the aspects of all the assessments of cap integrity and CCS we do is really to look at the faults. The faults have been created in the past by paleo stresses, and they had eventually time to heal, so a good cementation have happened, a good gouge it's in place, and they might not be transmitting fluids. They are sealing faults. However, we're going to inject pressure. We're going to increase and raise that pressure from the original one. And that situation may change the scenarios from stable to unstable. So here we're showing two examples of two different fields where we mapped in the major faults. And we are calculating here by the color scale what we call the critical injection pressure, which is basically the pressure above the pressure that is originally there in the reservoir and can be achieved before the fault comes to a state of a probable slippage and creating a breakage through of that gouge material that can increase permeability and lead to fluid flow through that one. So you see that there are some regions in red that they are more prone, they are very close, they cannot really take much excess of pressure, while other regions here in blue, they can really go and take much more pressure. So if we're thinking about a CCS project in a scenario like this, it would be prudent to kind of allocate our injection wells close to the blue areas and not really very close to the red ones. This is an example of an offshore field that, let me maximize this. So this is a cross section of the field where we have, you can really see there are some faults, and this is the main fault of the field. This is an oil and gas field offshore where injectors and producers were in place, and injectivity have been taking place for a few years, and pressure has been getting a little bit higher than original one because of that injection. So at a certain point, one extra well was to be drilled in this location and found excessive pressure that was not really expected. That excessive pressure created a scenario for fracking the well unintentionally, and that fracture became uncontrolled to the point that somehow connected to these major faults, and the scenario was really that those faults, fractures combination were able to find a way to propagate and reach the sea floor, because the excess pressure at that location, at that depth, was enough to reactivate the fault and propagate all the way up to the sea floor. And if I may play this video, you see a very nice ROV image when you drop the robot to kind of capture. And that's the signature of the fracture at the sea floor. And that's what you see are bubbles of oil coming from that fracture. And this is the result that at the end of the next day, you can really see a sheen of oil floating around in the ocean. So we don't want that scenario, because if our intention is really to keep our CCS safe and the high integrity, we need to keep the CO2 down there in the subsurface. We cannot allow for this, because this would compromise the main objective of the project. So speaking of a real case here of the CCS project, this project called INSALA is a project in Algeria in Africa. It's a well-known project. There are dozens, maybe hundreds of publications of this project, not only geomechanics, but many aspects. But you can find a good chunk of geomechanics, because there is some features that happen, situations that have been extensively studied. So for the purpose of having a context here, how we sit in relation to the geomechanical environment, we are under a strike-slip faulting regime, where we have the vertical stress as our intermediate, and we have a great anisotropy, stress anisotropy in the horizontal plane. The direction of the minimum stress has been characterized as a northeast, southwest, and here is pretty much the magnitudes that some of the studies have been kind of putting together and to come up with those numbers. Because before you do any evaluation of the risks or history matching or modeling of situation that may happen, you need to know the magnitude of the stresses and also your pore pressure. So here's a representation giving a top view of what is this project, right? So this is a gas production field, crash bar, and we have producers here as these horizontal lines, and the three injectors, as these red sticks here indicate, placed. And you see the gas water contact here, the orientation of the stresses. This is more or less the size or indication of the picture that you may find out here. And as injection started and pressure started to increase, this field has extensive monitoring from microseismic to tilt meters and also INSAR satellite data. This is a very good and powerful tool because you can monitor over time. It's like our Google Maps, right? When you see satellite image, and then you can see how your street has been evolved. The trees have been growing over time when they take pictures at the different time steps, like in 2000, 2010, 2020. So this is what INSAR can do for us. So in these blobs of blue colors here, they pretty much indicate that these regions very near and around the injectors, they will experience up to 5 millimeters a year of ground heave, an uplift in the ground surface. And then you may think, but this is not too much. But remember that these deformations are a reflection of what is going, or it's happening down there at the reservoir level. So what you see in the surface is a really small magnitude of what's happening down there. But still, it's enough to create problems, as we see in the next slide. Just before we go there, I want to highlight that there is a fault region in this in around this KB 502 well that pretty much was intersected by the well. So here the problem is, it seems to be the pressure. It seems that the reservoir was not extensive enough, and the pressure started increasing. And before they knew it, this fault region was really becoming more prone to slippage. And that's really what the models and the data observation has been showing. For example, there has been more than 5,000 microseismic events reported at this location. And when we put together those microseismic events with the flow regime analysis of the well, you can really see the data showing that as the microseismic events intensity increases, that really coincides when the pressure around that well was coming higher and higher and became above the minimum horizontal stress. So the interpretation of the data and the modeling really kind of points out that both tensile and shear mode failure really happened around that region of that fault. And that probably was the reason, and it is the main interpretation so far for how that well really became like unstable. In other words, so if you are still planning to inject the well, you cannot really continue at that pressure level, because every time you do, you're going to have fluids migrating through that fractured faulted zone. Now moving to the second point, which is the thermal impact. So in Salah was really a pressure impact. This next one is going to be more on the thermal stress impact. So as I mentioned before, the thermal stress is really significant because we are really bringing cool fluids down to the subsurface. And if this is our original temperature down there, and this is a representation of your original stress, by the time and you continue for decades of injection of a cold CO2 into the rock, that cooling effect is going to be creating this stress reduction. And this is very well established in geomechanics by the thermoelasticity or thermopore elasticity. And this is pretty much an equation that you can have a clue on how much is the thermal stress effect. So you have your Young's modulus, which is the deformation parameter, times your thermal expansion parameter, the delta T, the difference in temperature between injection and in situ, and Poisson ratio. So you can really see that regular parameters here that we find most of the time, we can really create like a 250 psi or more, depending on how much the thermal parameter the rock is. I'm kind of giving an explanation on this here because you're going to see how this is important and critical in the next example. Northern Lights, it's a project in the Norway, offshore project, and it's an extensive project, too, probably bigger than in Salah in terms of modeling, monitoring, studies. And as a comparison here, I would like to highlight that we are under normal faulting. In this case, we get our overburden as your maximum stress in the field. And the orientation is really that your sigma 3, or the minimum horizontal stress, is up to the north in this case. Again, here, a good idea of the range of the stresses. As I mentioned before, maximum stress sometimes is difficult to really pinpoint it. So in some cases, the best what you can get is a range. And the original pore pressure, again, in this case, was hydrostatic. So the authors of this study, they were really concerned about the thermal stress impact on the operations for the lifetime of the field. So what they did was they did a finite element simulation that they coupled the thermal hydromechanical process, in other words, temperature, pore pressure, and stresses together. And this is like a cross section in terms of the model. At the very left side here, we would have our injection point location. Johansen is the intake formation, but the Cook, the green one here, is the one to be the permanent storage because the CO2 is going to migrate by buoyancy to the top part here of the reservoir. And the Drake formation is your cap rock, basically. So they knew that they are going to bring like a 80 degrees difference Celsius, and that's much more than Fahrenheit, as injecting into this reservoir is going to happen. So the project is expected to kind of last for 50 years, 25 years of injections, but 25 more years of monitoring or modeling in this case. And they're really concerned about, okay, if we're going to be injecting through the Johansen, the migration is going to happen here. What's the cooling effect is going to be at this interface with the Drake formation? Is the pressure that is going to be sitting here at the Cook is going to be transmitted little by little? Of course, Drake formation is a shale rich formation, but shales are not impermeable. They are low permeability. Over time, they really can take pressure diffusion into them. So what about the temperature? How much the stresses are going to be changing in the reservoir and also in the cap? So here are the results of the simulation. They simulate the temperature change. As you can see here, in very near the wellbore, they can cool down up to 80 degrees Celsius. And as the plumb kind of moves, this temperature change is not that too much, but it's cooling down like 40, 20 degrees. And the pressure is not as great because, as said, shales are very impermeable. However, near the wellbore, you still have, after 50 years, some pressure increase. Like in this case, you can have up to 80 bars. In this case, the scale is bars, which is equivalent to 8 megapascal. So after they have calculated the temperature and the pore pressure change, they went to check how much the stress is changing. So same picture here, same idea. The green is the storage formation, the orange is the cap. Vertical stress is the black one, minimal stress red, and the pore pressure is going to be the blue one. Original values are the dashed or dotted points, and the change after the injections happen are the solid lines. You can see that in the overburden, the vertical stress, the changes in temperature and pressure create some sort of arching, but not significant. However, when we really look at the green formation, look at what happened, that this is the original minimal horizontal stress, and because of the cooling effect, they can expect the minimal stress becomes lower than the pore pressure. This is a scenario that you create for hydraulic fracture when you have a tensile stress present, where your minimal stress now is in tension. So they're going to crack the rock by injecting into this reservoir. You can see here in the pore pressure that the pressure is not really changing much because likely this reservoir is too extensive for the amount of CO2 they're planning to inject. That's not going to create an excess of pressure. However, all these changes in stresses are created by temperature changes. And then you see here that you are cooling down the cap rock too. From this point here, your pore pressure really reduces to this point. So the pore pressure in shales, they respond to temperature much more than the pressure change itself. So it seems that, yes, a fracture condition has been created in the reservoir. So they're expecting fracture condition in the reservoir. However, the minimum horizontal stress in the cap rock never really touched or comes below the pore pressure. In other words, it seems that a scenario for cracking the cap rock in tensile mode is not going to happen. However, there are usually two main modes of rock fracturing. We think about the tensile mode most commonly, but the shear fracture is also very important. And because of the difference between this overburden minus this minimal horizontal stress, if you are familiar with the Moore-Coulomb theory, that's pretty much the difference what creates the stress anisotropy or the shear stress. So now you have increased your shear stress that was this difference here from this difference originally to this difference here. So, and then you calculate how much is your maximum shear stress compared to your shear strength. In that case, it seems that for us, some regions in the interface between the reservoir and the cap, we're going to meet that criteria of a local factor of safety greater than 1. In other words, your shear stress is going to be greater than your shear strength here. However, this is the possibility. But the authors of this study has been kind of done further studies, and they have done some probabilistic analysis and trying to find best worst case scenarios to really see how much is the probability, which is not going to be discussed in this case. But they really claim in the work that's not going to be a high probability, although the possibility is there. So the takeaway from this short presentation today is that geomechanics is really critical for a CCS project, because in order to maintain the integrity and the safety of the operation for the lifetime of the project, we really need to understand where we're sitting right now before we start doing the operation and where we can go, because we may want to go to 1000 psi injection excess pressure, but can we really go there and it still stay safe? Or are the faults really going to be stable all the time? What about the temperature difference? Is going to be greater enough to create some stress changes that's going to put faults or the cap integrity at risk? So those are the things that geomechanics really can help the project to determine. And when we put in the context of other parameters or studies that are done in terms of the cost and the project impact, you can really see that geomechanics is really cheap, if you will, compared to the project impact that adds. So, for example, if you compare that with 3D seismic, that usually is a very expensive type of data to collect, and of course has a very high impact too. So geomechanics is really cheap. So it's a really not nice to have, but must have, because it's really your insurance ticket for now and the future. I just want to go brief through the reference here. If anybody is interested to check some of the features that I mentioned here, most of these papers are open source, so you can download, go and check to these links and download and read a little bit more about these studies. And there are many other features that I would like to cover and how we really do this type of model, but our time here is really limited, but I would like to take questions if I have some. Thank you very much.
Thank you. I'd like to remind the audience you are muted, but you can ask questions using the GoToWebinar question feature, and you will be anonymous. So here's our first question. Could you expand a little more about the alteration of the mechanical properties of the rock? Which property is more affected and how to minimize the alteration?
Very good question. And that will depend on, in this case, I'm showing just a case for the limestone, but there are other studies already done in siltstones and also shales and sandstones. That will really depend on how much and how many of your minerals in the intake rock are really prone to be dissolved by the CO2, right? Let's say in this case, we have limestone that's a calcite-rich rock. So that's gonna suffer probably the most or the highest alteration with this injection because of the acid. And as you can see in this example, you really is gonna see a difference in ultimate strength that, let's say, if this was like a 16, 17 megapascal, you drop it that almost to 9. It's almost a 50% drop in the strength. And also the deformations. So if you're expecting to see a deformation of X, now you're gonna maybe have 2X because of your Young's modulus have dropped quite a lot. So in terms of properties that will change, both ultimate strength and deformability are going to be impacted. But again, if you have a sandstone that's more quartz rich, you're not gonna see that much. But if you do have a sandstone that has a good chunk of a calcite, or if you have siltstone that have more minerals that are more prone to alterations, that's going to be the case. This is a very type of a simple experiment that can be done. You can get an intact rock in the lab, you test it, and then you create your solution at the concentration that you might expect for the project. You immerse your rock into that solution for a couple of days, expect some changes, and then you repeat the test, and then you see how much difference you have. So with those parameters, we can create some sort of a safety factor into the modeling, right? Because you can start your model with, let's say, with the original parameters, and as your time goes by, you can implement some sort of a decrease function from strength and from the formation parameters.
Great. Here's the next question. Is it operationally or economically feasible to heat the CO2 prior to injection? I imagine deep water would prove challenging, but perhaps in shallow water or onshore, have many studies been done on this?
Very good question. I hope I was able to kind of give the insight that this is not a linear problem. In other words, the most comprehensive characterization that we do at one location, we cannot really, let's say, lift and shift to another location. If you are in an offshore environment, you may be at a similar situation than onshore, but most likely going to be different because the pore pressure environment is going to be different. Let's say if you're thinking about Gulf of Mexico, where we have a lot of old aging reservoirs that may be kind of people looking at those places to be candidates for injection. They have been under severe depletions, and some of them, they have been originally at a very high pressures, and now we are at a very low pressure. So the stresses had changed. So how much right now can we go? And that will depend how much we need the minimal pressure at the reservoir to be for the CO2 to be feasible to be injected. I worked at a project some years ago that it was a very shallow project. It was like 1 kilometer deep, and the reservoir has been severely depleted for 40 years. So the pressure was so small that before they started injecting the CO2, they have to raise that pressure to a level that was above the original pressure 40 years before. But that location had 5 major faults extending all the way to the surface. And the main concern was, okay, how much can you keep pumping before these faults get reactivated? Because if we reactivate the faults, we're not going to be able to maintain pressure, because if you elevate the pressure, pressure leaks out through the surface. So it's not a simple question. That's why this geomechanics characterization has to be done on a one-by-one scenario to make sure we are not guessing things here.
There's no rules of thumb to apply.
No rule of thumb, yeah.
How could you estimate the seal of the cap integrity since the reservoir and seal above have different gradients?
Very good question. Here we're speaking, let me get this picture here. In terms of what we call integrity, here we're speaking about mechanical integrity. Right? Of course, when we compare this with the regular seal capacity that usually in exploration in oil and gas, we think about the capillary entry pressure. So we're not talking about that scenario here. We are talking about a more like a hardcore mechanical scenario here. Yeah, you're right. So eventually, the stresses in the cap rock are not the same in the reservoir, because first, usually this is a shale, and this is a permeable formation like a sandstone. And because of that difference in flow properties, the stresses and pore pressure evolves at different paces and rates. So, and that's why it's so important to characterize both. In other words, we have to run well logs through the overburden and the reservoir. We have to take core from the cap rock and the reservoir. We have to test both, and any models have to include both at the same time. A simple reservoir model, let's say, turning off the cap rock here for flow permeability, is not going to tell us much here in terms of stresses, because we're just making an assumption. Yeah, you know, my cap seal is a shale, low permeability. I'm not going to have flow here. However, in terms of geomechanics, we need to include that. And as you see in the results, the injection into the reservoir, because of a thermal diffusion into the cap rock, just the conduction, right, happens, is going to change the stresses here. So we do need to take tests, measurements, and modeling in both. And that's the way we do in geomechanics. So you can put numbers in quantification, right? So not really in terms of a quality, but really in amounts.
Next question for the LFS calculation: how do you assess the parameters for cohesion and coefficient of friction?
Very good question. If you do have core, and in this case, this study has been extensively studied. There are many other publications out there that you find. They do have a core test for, it's a triaxial type of test that you really, these two parameters, like if you look at cohesion and this angle here, if I migrate back to this, yeah, this is what we're gonna find. The intersection of that line is gonna be your cohesion, and the slope is your friction angle. So this parameter here, so it's gonna be your friction angle, and 5.6, of course, this is not exactly cohesion because this is effective actual stress, but it's a function of that. So that's the way you characterize. So you take a bunch, or a couple of, in this case, 3, 6 tests, and then you find the best fitting, what we call the Mohr Coulomb envelope, the strength envelope, and that's what mathematically expresses the shear strength of the material.
Next question, how does one monitor the success of the CO2 injection? Is it recommended to run 4D seismic, or are there other tools that you can use to monitor the plume?
Excellent question. So yes, in terms of monitoring, 4D seismic is a way of doing, because you really can see how your plume is extending, right? Because let's say you assume that your limits or boundaries of your container is around this area here in your model, in your characterizations, but we have uncertainties. We always have uncertainties. And monitoring by time lapse for this time is a way of doing. The other way of doing, and in a much cheaper way, is the satellite image, because you can tie, for example, if you have specified that your container has an X dimension, then you know that the amount of volume that you are pumping inside of that container, you create or generate an expected displacement or no displacement at the surface, right? So if by any chance you start seeing things that are in disagreement with what you expected, then you start seeing that, okay, if I'm not seeing in satellite image, for example, a ground heave, it seems that maybe my reservoir extension is greater than I thought in the beginning, right? Or maybe I'm having migration of fluid through the cap rock into a shallow horizon. So you can have a set of monitoring tools like pressure gauges. You can have satellite image, which is very powerful, cheap, and then you can have this permanently, constantly monitoring for you. So for the seismic, of course, is very valuable too. However, it's costly and takes time, right? So this is the way that you really can do. And then if you tie that back to geomechanics modeling, for example, in this case here of Insalar, they have done a very great work of relating how much of ground heave they saw with the size and amount of displacement that was expected that the faults would provide for creating that type of displacement at the surface. So you can really go back and forth, model and tie this back, and have it's like a history matching for the reservoir simulation, right? You get some measurement and you run your model again to see how things are progressing. And as you go by, you adjust and try to reduce the uncertainties.
You mentioned that CO2 can destroy the cementation in the reservoir. How fast does the reduction of mechanical properties happen when they're exposed to CO2?
Well, I don't have a rule of thumb here for this case, but that will really depend on the amount of calcite or more prone to reaction material. I don't recall from the top of my head what happened and how long these experiments taken. Of course, that should be mentioned in the reference, and here's the reference for us to check later. But it can be, we can really relate this to some home experiment that we can do, right? We can get some sort of rock pieces, like say calcite rocks, and then we can just dump them into, I don't know, white vinegar and see how fast that go. So this really, when it is taken to the lab, it really give you a notion of how much that amount of rock, which is limited, a sample of rock, is going to be altered, right? Because at the end of the test, you can really, well, at the beginning, you can measure everything. You can measure porosity. And in actually this paper, they measure two things. I'm just highlighting the geomechanics, but the title of the paper is really injection effect of on geomechanics and flow properties. They also measure the changes in permeability and porosity. So in that amount of time that they immersed the rock, like days or weeks, they can really see, oh, that amount of material was destroyed. And actually, I remember that in the paper, they mentioned that they have an inlet and an outlet in the sample, right? So where the fluid is coming in and where the fluid is going out. So they really realized that the dissolved material at the inlet was actually deposited at the outlet. In other words, you may enhance your permeability near the well, but you may start losing permeability as those fines that have been released are transported by the injection, right? So in later, you're going to decrease your permeability, which is going to maybe favor the fracking of the formation because now you have a less permeable rock, and then the pressure can increase faster than you expected. So that is not really a rule of thumbs, but those things can be quantified in the lab.
Very complex. We've been talking about CO2. Have you evaluated the leakage mechanisms due to hydrogen storage projects, both injection and withdrawal? Do you have any experience with the geomechanics effects of hydrogen?
No, that's a good question. And actually, I don't recall that I have, for up to now, seen any published work done on hydrogen. I think hydrogen has become a little bit more, I would say, popular in the last couple of years. And if there are studies, I'm sure there are studies ongoing right now, but I haven't seen that one published yet. There should be some.
The 4D seismic at Schleipner Field shows barriers have segregated the CO2 into layers, possibly increasing the storage. How could geomechanics analysis characterize the potential for these types of baffles and how injection could preserve their integrity?
Very good question. And that's why we call coupled phenomena, right? As we change the stresses, we may change flow properties too. For example, in here, we have the permeability. There are many studies done in the past from oil reservoirs that we can see that depending on the rocks, if the rocks are more like high porosity, or if they have a lot of natural fractures, they may be more sensitive to stress, what we call stress-dependent permeability. And again, this is the type of characterization that can be done in the reservoir. For example, in the unconventional shales, it's very common for the labs to do conductivity tests in the fracture, right? They kind of really see how much the fractures close as the effective stress increase. And then they create permeability equations that the reservoir engineers can put into the simulators. In case of geomechanics, we can have this in what we call a fully coupled simulation. Like we have a stress simulator coupled with a reservoir simulator. And then once you establish those stress-dependent permeability, as the flow change across the reservoir, the pore pressure change, that goes and feeds back into the stress simulator, which updates the stress and rechecks how much the permeability should change. It's a complex phenomenon, but can be done, and there are tools available for that.
The next question relates to wellbore integrity. Before the injection of CO2, what study needs to be done to evaluate the cement behind the perforations where oil has been produced for a long time?
Good question. Yeah, right now there is a big debate about how can we repurpose, right, old wells that are not producing anymore from old oil fields, and can we use them for CO2 injection? Well, if we go back to what we're talking about here, the EPA guidelines, they are the most strict rules regarding permitting wells. So that well that was put down in the ground before for injection or likely a producer from oil and gas, right? They were not really up to the highest standards of the EPA when it comes to class 6. They may have been like a class 3, class 4. So in the cement that was used and some other characterizations, for example, when you are permitting, for example, a well to be drilled for oil exploration or production in the Gulf of Mexico, there is no much requirement other than the pore pressure and fracture gradient. But if you want to repurpose those wells, you really have to go and check for all these things. First, yeah, there are well logs that can be run in the wells, like cement bond logs, to see if that cement that was used for completion that well few years ago, is it still good? They have channels or not? Because the wells can be the major source of leakage in a CCS project. And there are some studies already debating if it's worth it kind of repurposing the well, or better kind of start from the scratch and drill a new one. Depending on the situation, you might be able to recycle, but depending, in some cases, likely a brand new well should be the best solution.
When you look at a potential region for CCS, where do you begin in terms of assessing relative potential and safety? I thought this was the lateral extensiveness of the cap rock, and I assume geomechanics and 3D seismic are a powerful combination to figure this out.
That's exactly correct. So of course, in here, I just have a cartoon, a cross-section 2D. But these studies, usually they start from a 1D point of view, right? You look at the well bores that you have already in that region, and you do 1D models in those wells. You look at the seismic characterization, faults have been mapped, and things like that. And once things start getting volume, you migrate this into 3D volumes, right? And then you get the 3D models that are really very similar to what you have for a reservoir simulation or a seismic volume. You bring that seismic volume into the geomechanics model, and then from those seismic velocities, you can derive deformation parameters like Young's modulus, Poisson ratio that are needed for the geomechanics calculation. Of course, those parameters have been calibrated to the lab tests, and there is a lot of pre-work that has to be done before you really start pushing the buttons and see 3D stress being calculated like this, for example. For us to come to this point here, there are months of work, like really trying to putting together all the well data, seismic data, reservoir data. But yes, you're right. So this is not really an isolated. Geomechanics is really more like a bridge that really connects engineer to geoscience, right? And then we kind of have flavors from both sides of the bridge.
It's definitely a multidisciplinary problem.
Definitely.
Well, we've had some wonderful questions today, so I want to thank our audience. Later today, you'll receive a link to a recording of today's webinar. You'll get an evaluation form, and you'll get a link to SCA's website with more information about the services provided by Everton and his team at Subsurface Alliance, including those related to CO2 storage solutions. Thanks for joining us. Goodbye.
Thank you.